All right, next we have Amir Shehata. He's been working with HPDD on the Lustre networking module since March of 2013. He's worked on the dynamic LNet configuration, multi-rail, LNet health, and resiliency features. Let's give a big hand to Amir.
Hi. Today I'm going to talk about multi-rail health. This is a project that we've been working on with HPE, with Olaf Weber. What I'm going to do is I'm going to start by giving an overview of multi-rail. It's been presented on last year, but just to recap it quickly. Then we'll do I'll give a slide on multi-rail performance on an HPE system. Then I'll dive into LNet resiliency and then interface health tracking, reporting, and then a quick summary. So what is multi-rail? Multi-rail basically gives the ability for LNet, which is the Lustre networking layer, to use multiple interfaces. This gives us two benefits, main benefits. One is to increase performance, and the other is to increase resiliency. So for large machines like the HPE MC990X, it's a 32-socket NUMA system. And large systems like this needs a lot of bandwidth, so they need to use multiple interfaces. Right now, before multi-rail, LNet could only configure one interface per network, one interface per LNet network. So this made the configuration very cumbersome. It also didn't provide any benefits, any NUMA benefits. For large systems, it's always, it gives a really good performance boost if the interface you send the message or the data from is NUMA, is close to the NUMA node where the memory is. So this is one of our goals, was to be able to be NUMA aware. And also we wanted to be able to allow different types of hardware to be used, like Intel OmniPath, IB, Ethernet, and we wanted to simplify configuration and increase fault tolerance. So before multi-rail, this is the type of configuration you would need if you had a machine with multiple interfaces. You would have to configure multiple LNet networks and put each interface on that LNet network. And then for the machines which did not have multiple interfaces, you sort of had to fake the connections to those networks. This was obviously a lot of configuration problems here. So what our goal is to reduce the configuration burden and allow multiple interfaces to be configured on one network, sort of like in this diagram there. So what does this give us? This implementation of the LNet layer allows multiple interfaces to be connected to one network. It allows multiple interfaces to be connected to different networks normally, and all those interfaces can be used simultaneously. Because it's an LNet level implementation, like I was mentioning before, those interfaces do not have to be the same type of hardware. You can have OmniPath hardware, you can have IB, EDR, or whatever. You just have to configure the OmniPath and the EDR on different networks like O2IB0 and O2IB1, and then MR code is able to select the interface. So if you have two peers, both of them are on the two different networks, those two interfaces can be used simultaneously. So quickly going over the basic configuration. First, you have to configure the node with the interfaces. So for example, O2IB0, you can configure IB0, IB1, and IB2 on those on the O2IB0 network. And then you have to tell the network, you have to tell the node the peers interfaces, and that the peers are LNet, are multi-rail capable. So to do that, you configure it something like this here, where you say on the node you tell it peer B has 3 different interfaces and it's multi-rail capable. Now that the node knows the interfaces of the peer, it can use those interfaces in round robin, or it can use them. Well, there's a selection algorithm that goes on. So first it looks at the credits per interface, per network interface, and it selects the one with the most number of credits available. And if all the credits are equivalent, then it will use them in round robin. Of course, so all this work up to here, all this work is actually on 2.10 right now, and it's available for people to use and try. On the multi-rail branch, which the link is there, we know that having to configure a large cluster with a whole bunch of peers manually can be very error prone, and it's not the easiest thing to do. So what we did is we have a dynamic discovery protocol which allows a node to discover the peers around it on the first time it talks to it. So for example, let's say you have 2 peers, peer A and peer B, and peer A is trying to talk to peer 2, so for the peer B. So the first thing it does, it pings that peer with just a normal ping, and peer B will respond with set all of its interfaces and with a feature bit mask. If the multi-rail feature bit is set in that mask, we know that the peer supports the multi-rail feature, and then we do a push of our interfaces to the peer. Once at this point right there, both the node and the peer know each other interfaces, and they're able to use them simultaneously. Whenever there's changes locally on the local set of interfaces, say somebody uses DLC to add a network or remove a network or add an interface to a network, then this will result in a push to the peer to update it with the node's interfaces. So this work, like I mentioned, is in multi-rail branch right now, and it's available for review, so please go review it, test it, it'll be good. Just to cover quickly some performance numbers we got. So we tested, or actually HPE tested on a 32 socket Intel Xeon processor with 16 terabytes of RAM. It had 8 OmniPath interfaces and 8 object storage systems, and each OSS had 4 OSTs. And the rest, the important part here is they used a utility called dplace to distribute the 520 threads among all 32 sockets so that we can get an even NUMA distribution. And then we can see the performance benefit this way. The theoretical maximum for sequential writes was 34.5 for that system. Sequential reads, theoretical maximum is 86.4 gigabytes. With multi-rail, we're able to achieve 93 of the writes and 80% of the reads, so 31.9 gigabytes and 68.5 gigabytes for sequential reads. These numbers were reported are the best of 3 consecutive runs. So you can see that it gives us a good performance boost with large systems. But then comes the next, this is just a graph of how the performance increases as you add interfaces. So you start with 1 interface, you add the 2nd, 3rd, 4th, up to the 8th interface. So now that multi-rail is there, we need to be able to bring in some resiliency. Right now, even if a message fails, we're still going to report it up to Lustre and the portal RPC and then Lustre, and then this can be, the error handling can be heavy at this point. While now that we have multiple interfaces available to us, we should be able to try different interfaces before we declare the message failed. Just to say quickly that this is we're currently working on this. We have the design in place, and we're going to move on in the development soon, hopefully. So to cover quickly the LNet messages, there are 4 different types of LNet messages. There's the put, the ACK, which is a response for the put, get, and a reply, which is a response for the get. This gives us 3 different combinations that we need to handle. Just put by itself, put that requires an ACK response, a get which always requires a reply response. So what are the resiliency goals? We try to try all the local interfaces before we declare a message failed. Obviously, we can't keep retrying until forever. We have to have an upper limit, time limit, before we say that this message has failed. And we want to implement the resiliency logic at the LNet level so that we're able to fail to different types of hardware rather than like implement it at the LND level and only be restricted to either IB or OmniPath or whatever. So our strategy here is to worry only about the next hop. So it's a resiliency against failure to the next hop directly. An LNet network can be directly connected, or it can have routers in between the different endpoints. LNet resiliency ensures that LNet messages are delivered to the immediate next hop. And then the immediate next hop worries about making sure that the message is delivered to the following hop and so on. There are 2 types of failures that we need to be able to handle. There is the what we call soft failures, and there's hard failures. Soft failures are failures that are recoverable, and hard failures are failures which you can't recover from until you get an event saying that the interface is up again. I'll dive into that, but I just wanted to give a quick intro on what soft and hard failures are. So now I'm going to cover how we plan to deal with the 3 combinations I talked about: put, ACK, or get reply. So for a put message, that indicates that we're about to RDMA some data to the peer. This is the simplest LNet message, but because it has no response, if we're successful in sending the put message to the next hop, there's no way for us to know whether it succeeded or not. So whoever requests a put, or when Portal RPC requests a put message, it needs to be able to make sure that if the expected action is not taken, it will recover somehow. This is outside the realm of LNet. For put plus ACK, the sender of put can actually explicitly request an ACK, and the ACK message is generated at the LNet layer once it receives the put. Since LNet expects an ACK, we are able to start a timeout once we send a put, and if the ACK is not received within that timeout, then we propagate up a message, an event saying that it has timed out, and then the Portal RPC can do something with that. Get plus reply is same idea. A get always expects a reply, and reply sometimes returns the data that's been pre-positioned by the upper layers. So if LNet never receives the reply at this point, again, it can time out and propagate an event up. So like I was saying, like when we send a put or an ACK or a get or a reply, there are 3 types of different failures that we have to deal with. There is the local interface failure, so somehow we're unable to put the message on the wire. There is the remote interface failure, where we send the message, but the remote interface never responded or is down somehow. Or there is a path failure, where we know we sent a message, but we're unable to determine whether the far end received it. So these are the 3 different types of failures, and like I was saying, there's soft failures and hard failures in this The hard failures are mainly for the local interface because we can receive events, and I'll go here right now. So for example, for local interface failures, you can receive events from the LND layer saying IB event device fatal or event port error. So on those events, we know that you can't really use that interface anymore until there's a message or there's an event saying that the device is available for use again. So LNet can refrain from using those interfaces for any traffic. It will try to retransmit on other interfaces if they are available, and if they aren't, then we fail the message. If there are available interfaces, we keep trying to send on the different interfaces until one succeeds or the peer timeout expires. For remote interface failures, there are multiple reasons the remote interface can fail. For example, we try to look up an address, or the address is wrong, or there's no route to host, or connection cannot be established for some reason, or it was rejected due to incompatible parameters. All these are possible reasons for failure, but they are not necessarily hard failures. They can be recovered from. So in this case, the local interface is working properly, but we can't establish a connection with the remote interface. So LND will report this error to the LNet layer, and the LNet layer will attempt to resend the message on a different interface. If none are available, then we fail the message. The path failure, which is the more interesting case here, the LND implements its own protocol to ensure that messages are received by the far end LND. So when LNet says send a put message, there's a sequence of LND messages that goes across between the two, the local LND and the remote LND, to ensure that the put message is received. So when LND messages is sent, there is a transmit timeout that's associated with this message, with the LND message. And if that transmit expires before, it depends where it expires, we're able to determine whether there was a problem locally or remotely. So these are the cases that we have to handle. So the message is on the sender's queue, but it's not posted within the transmit timeout. In this case, we know that it hasn't even left the node yet, so there is a problem locally, and then we'll handle it as I covered it a little earlier. The message is posted, but the transmit never completes. So at this point, we don't really know where the error is. We know that the message was sent, but there could be a problem either somewhere in the switch, a router, or something that's preventing the message from reaching the other side. The message is posted, but the transmit completes, so we know that it got received, but the remote never acknowledges with an LND message. In this case, we know that there's some problem with the remote, and we're going to try to handle it as if it's a remote failure, by trying a different interface. Otherwise, in the second case that I was talking about, where the message is posted but the transmit never completes, we'll just try a completely different pair of local and remote interfaces. We want also the ability to intelligently select the interfaces that we send from. So what we're going to do is we're going to keep a health value per local and remote interface, and whenever there is a soft error on either the local and remote, we'll decrement that interface health value. By doing that, the next time we try to select an interface to send from, we look at that value and we select the one with the best health. That will give us the ability to select the best interface available for us. And if the interface is consistently failing, then it will consistently have a low value, and in the long run, we will favor it less and less. All this, so now with LNet Health, there is a slew of different information that we can pull up using LNet Control, which is a utility to configure LNet. We're going to provide the ability to pull this information to view the health of a specific node and its peers. This will enhance the ability to debug clusters when needed, and it can be used by any management GUI to display it. So in conclusion, LNet Multi-Rail allows us to use multiple interfaces on one node, and that increases the bandwidth. This allows servers to scale by adding more interfaces. Instead of like buying new interfaces, you can add extra interfaces. Useful for large clients, like we said, and it adds the NUMA capabilities. So we're able to select the interfaces that are NUMA that are close in the NUMA topology. And like I was saying, the base MR is in 2.10 right now, and it's been tested and should be good to use. Dynamic discovery simplifies the configuration for multi-rail LNet. This code is currently available for review and testing, so go ahead and use it. LNet resiliency builds on top of this multi-rail infrastructure, and it allows resending LNet messages to different interfaces on failures, and handles delivery to the next hop, which is in charge of the further hops. Again, this is implemented at the LNet level so that it allows us to use different types of hardware. So this concludes my talk. Any questions? So there is one here and one there, I think. I can hear you.
So, can you control how sick an interface is before you drop it for the health?
Can you control how sick the interface is?
Yes, because you were saying you would evict it when it reached a certain level. So I was wondering, can you control that?
We don't evict it when it's certain. Like we prefer it less. So, for example, if you have a bunch of interfaces which have low health value, we'll still select them if it's just the best one that's available to us.
I just mean that some sites might be more tolerant to hardware failing, and they don't want to remove it, for maintenance reasons or others. Where other sites might want to fail right away.
Fail to a different interface right away.
Yes. Yeah.
We haven't considered that point, but we'll take it into consideration in the design.
Thank you.
Thank you.
Amir, thank you for sharing this with us. So you didn't talk about LNet self-test. So will that be changed for this? For debugging and testing with this multi-rail for the LNet self-test?
Yes. So LNet self-test right now we use it for testing multi-rail. And we will modify it so that we're able to test this type of failure as well.
Okay. Yeah, thank you. So that needs modification, right? That self-test will be modified.
Yes. Yeah, we have. Yeah, the code is under our control, so we'll modify it to be able to test this feature.
Okay.
Hi, Amir. I have a question about how routes affect this health value. So how do you keep, routers that may intermittently fail from backing up onto that interface health value? How can you differentiate between, spotty routes and the interface health?
That's why LNet health is only for the next hop. So say you have a node and then it's followed by a router and another router and so on. So that node that's initiating the message, it knows it's sending to a router. So it's only considering the router's interfaces and not the endpoint or the last value interface.
So if I understand that correctly, then if you are a peer and you have a dozen peers to communicate for any network, you could use any of those routers.
Yes.
If a remote interface was bad, then you can actually still use that local interface to send to the other 11 peers, and you can distinguish that.
Yes.
It doesn't back up into that. Your interface for that particular local interface will not have a negative health value.
No, because, okay, so let's take the situation where, for example, you have an endpoint which has a bad interface, right? But you have multiple hops in between the initiator and the final destination. If the peer or if the routers are good, we'll still send a message. It's only the last router before the final destination that will try the different interfaces of the final destination, and will start marking the health value of the interfaces of that final destination, and we'll try the different interfaces. If that fails, the peer will time out on our side, and then we'll try to retransmit, selecting a different probable router path.
I have a quick question. So how about the transition timeout such kind of error? So because network congestion sometimes make high latency, in that case some time cover. So in that case sometimes error, but sometimes okay. How do you control?
Are you talking about the transmit timeouts? You can control the transmit timeouts are configurable. So for, say, for example, you start noticing that the transmit timeouts need to get increased, so that you can configure them to be longer.
Yeah, so statical setting is not so.
Sorry?
Statical value of the setting is not so.
Yeah.
So you need some improvement, such kind of
Yeah, I think you need some sort of experimentation in order to try to understand exactly what the transmit time is.
Yes, please.
Hey, Amir. I think there is already a retransmission at portal RPC layer. So it means we are going to have two layers of retransmission, one at the portal RPC layer and one at the LNet layer. So how is it going to behave together? Are they aware one each other or?
Yeah, so the portal RPC, I think that transmits at the RPC layer, RPC level, while we retransmit the messages which compose the RPC transaction, right? So you will need to be able to adjust the timeouts properly so that the peer timeout, for example, can be longer than the RPC timeout. Does that answer the question?
Thank you.
Yeah. So I wanted to ask, so you're using timeouts as a way to gauge the health network. Have you designed it to be more flexible than that? Because one of the things that people have wanted for a long time is to be able to be aware of the underlying hardware failure states. Like, it's possible from the InfiniBand layer to get the state of the hardware and then weigh that into failing it over.
So we're restricted with the type of events that we get from OFID, right? So for remote interfaces, I listed some of the errors like an address error or whatever. Other than that, we don't have much information. For the local interfaces, there's only two events like the IB port error and the device error. Unless we're able to modify OFID, and I've been kind of looking into that a little bit, but there is, for OmniPath, there is a different set of information that we can get out of the hardware, that if we're able to propagate up, then we can use that intelligently into maintaining the health information for the interface.
And one of the other things people have asked for is the ability to remove the InfiniBand driver underneath the KO2 IB and LND driver. So
I'm not sure, remove it how?
Like module remove it.
Oh.
Yes, this is something they wanted to shut down the service on the node, and then they've always wanted the the KO2 IB LND driver to survive that instance and kind of shut itself down cleanly. And
I'll have to look into that. I haven't looked into that before.
I've looked at it. It's a very complicated process, but it's another consideration with this health network stuff.
Okay, thanks. Thank you.